All right, good morning, everybody. So yeah, today is everybody has a E6B. You got an E6? We got a pencil. You have a pencil, Delbert? Pencil.
Pen.
Okay, here you're gonna want a pencil to write on the back side of your E6B, so you don't leave marks on. You can erase that at a later date. All right, we're gonna do E6B today, the dreaded E6B. I don't know why everybody is scared of this thing for some reason when it comes to aviation, but it's such a dead simple tool. So simple.
Developing that was not.
Developing it was not a piece of cake, but everybody know what a slide rule is? Anybody not know what a slide rule is? Raise your hand if you don't know don't know what that is. Okay, so it'd be the younger people, and that's okay. So here's what back before there were calculators to do quick mathematical calculations that involved multiplication and division and powers of numbers. And you can't do addition and subtraction, but you could do multiplication, division, powers. You do things like that. And it was back in actually the 1600s, I think, that it was originally developed, was a slide rule. And essentially it is a number line, but instead of two number lines sitting on top of each other, but instead of them being the same unit, so one unit is this big and the next unit is that big, they were logarithmic. So each unit got smaller and smaller or bigger and bigger in a logarithmic fashion. And then by sliding these scales back and forth, you could do multiplication and division problems. And that became a slide rule. So, we landed on the moon, and, all the engineers and all the guys that were involved in getting us to the moon, the ones that designed the rockets and designed the spaceship and designed all that stuff and did all the calculations to get us into orbit and to get us to the moon, they didn't have calculators. You know what they used? Slide rules. They used the equivalent. They used these, but rather than being circular slide rules, they were linear slide rules. They worked this way. So that's all this is. It's a slide rule. So we are required to be able to do certain aviation-related calculations, obviously, right? We need to be able to do time, speed, distance, and fuel burn calculations, and calculate true air speeds and density altitudes and true altitudes and all of that kind of stuff. So we can purchase does anybody have a E6B, an electronic E6B? Did anybody purchase one of those? Okay, so you can purchase, one of those sporties. It looks like a calculator, but it's an E6B. And we have a lot of students that buy those and purchase those. And there's nothing wrong with that if you want to do that. The biggest drawback is that it takes batteries, so they can die if the batteries die. And if you're trying to fly and use it, it's bulky. It's hard to use with one hand. You have to punch numbers into it just like a calculator. This never runs out of battery. You can spin it with your thumb. You can do all the calculations you want. And it's easy to use, okay? And what I will tell you, if you haven't purchased an E6B and you're thinking about purchasing an E6B, you're looking at this and saying, wow, I'm going to go purchase an E6B because this looks complicated. I don't want to have to learn how to use this. You know what you're going to have to do when you buy that $150 E6B? You're going to have to learn how to use it. Because it's not a calculator. It's not punch, 10 times 5 in there. It's not. You have to learn how to use the electronic E6B. So why not just learn how to use this one that costs, whatever, virtually nothing, and it never needs batteries, right? So that's what I'm trying to teach you today, how to use this. They're not complicated at all. It does an awful lot of things that you will never do with it. And I kind of jotted them down because I can't even remember all the kind of stuff that it does. It does so many things. So, obviously it'll do temperature conversions, unit conversions, statute, nautical kilometers, Mach number, feet per minute, feet per mile. It'll convert volumes, gallons, imperial, U.S. liters. It'll convert weights, pounds, kilograms, oil weight, fuel weight. It'll do time, speed, distance, fuel burn calculations, density, altitude, true airspeed, ground speed, wind correction, wind direction, off-course correction, radius of action. It does all kinds of stuff. What we're going to typically do with it as pilots, from a practical standpoint, we're going to do one of these three, or a combination of these three types of problems, or answer these three types of problems when we're using either this one, or if you go buy the $150 Sporties one, you're going to do the same three sets of problems with it. That's just what you're going to do. So I want to teach you how to use this to do those problems, okay? So it looks scary when you look at it. There's a bunch of numbers and it spins, and it does some crazy stuff. And on the back side, it's got some other crazy looking lines all over the place and numbers everywhere, and it's really scary looking, but it's really not, all right? Here's the three things we're going to do. We're going to do rate problems. And when I talk about a rate problem, when I use the word rate, then what you need to think is time. Anytime you hear rate, there's a time function involved in this, all right? I'm traveling at a rate of speed. That means I'm going so many miles per hour, as an example. Or if it took me so much time to go some particular distance, then I can figure out what my rate of speed was, okay? So anything, when I say rate, anything rate related is a time function. How do we tell time? How many seconds are in a minute? How many minutes are in an hour? Okay, so 60 base is the way that we tell time. When we work with numbers, we have lots of bases. We could work, if you're a computer program, there's a base 2, right? On, off, ones and zeros. That's a base 2 set of numbers. You could have base 10. When we do mathematics, we use a base 10, right? Our number line is 0 to 9 or 1 to 10, however you want to look at it, right? So it's a base 10. When we tell time, it's a base 60. So anything in time is a base 60. When we use latitude and longitude, we convert it to decimal point, but it's generally a base 60. There's 360 degrees in a circle. There's 60 minutes in a degree, and there's 60 seconds, subdivided into that. So that's a 60 base system. So this accounts for both a 10 base system and a 60 base system. So I want you to, first off, set it up just like this, so that all the numbers are aligned, 11 and 11, 12, 12, 13, 13. Just set it up just like that. We're going to start with that. I want to talk to you about some of the things on here. All right, I want you to notice, and I'm going to refer to, there's 3 rings, if you will. There's 3 rings. And sometimes, and I'll try to use the same nomenclature, but sometimes I mess up. A ring or outer ring. B ring or middle ring, C ring or inner ring. So sometimes I'll call it A, sometimes I'll call it outer, sometimes I'll call it B, that means middle, C means inner. So you got 3 rings. You got the outside ring, A, the middle ring, B, the inner ring, C. So if you hear me say outer, you know I'm talking about A. If I say the C ring, you know I'm talking about the one in the middle, okay? All right, just because I know I'll use them interchangeably. This was developed by a guy by the name of Dalton in the 30s-ish. So it was widely used in World War II.
It could have been in World War II.
It was absolutely in World War II. Yeah, it was absolutely used in World War II. Yeah, different versions of it have been developed over time, right, to do different things, but it's all based on logarithmic number scales. Okay, and so anyway, I'm going to show you how to use this. So I just talked about 2 sets of number-based systems, 10 base and 60 base. So I want you to notice 10 is highlighted. That's a 10 base system, or 60 is highlighted. And you notice it says rate on it. Okay, so if you're doing any problem that involves time, any problem that involves time, are you going to be using a 10 base or a 60 base set of numbers? You're going to be using a 60 base, right? So you know right away, if you're doing anything where you're trying to figure out, hey, if I eat 5 apples in an hour, how many apples can I eat in 3 hours? Well, that's a rate question because you've got time involved in it, okay? If I'm flying at a speed of 110 miles per hour, that's my rate. So we know right away we're using that 60 number. If I flew a distance of 30 miles and I did it in 10 minutes, how fast am I going? Right away, there's a time involved, so we're using that 60 number. So anytime time in any form comes out of your mouth, 60, think about that 60. Okay. Primarily what we're going to use this for is always the 60. They have the 10 on here, and I'm going to show you how to use that, but you'll never really use it unless you just want to do multiplication and division using this, which I'm going to show you right now how to do it. So to use the 10-base system, it's real simple. If I were, I mean, it's incredibly simple. If I were to set up a division problem and I said, what is, well, if I asked you, what is 60 divided by 15? How would you write that on the board? Would you write it like this? Would you write 60 divided by 15? Does that make sense to you? Okay. What I want you to do, see how you can spin this? I want you to spin it so that the 15, this is the A scale, this is the B scale. I want you to put the 15 underneath the 60. I want you to divide 60 by 15. All right, and to do that, here's what we're going to do. So 60 is way over here. 60 is right here. 15 is right here, so move this over to here. So we're going to spin it so that the 15 is right over here at the 60. The 15 is at the 60. Okay. If I'm doing a division problem, am I working with a 10 base or a 60 base? So find the 10 and look at the number above it. That's your answer. That was your division problem. Okay, this is because this is a logarithmic calculator. All right, so you could do that with any number. Let's say you want to divide 17 by, I don't know, 5. Divide 17 by 5. So 17 on the outer scale, put 5 underneath it. There's 5. What's the answer? So we're 17. 17 divided by 5, find the 10 scale, is 3.1234 something. 3.4 something. See how that works? Okay. These kinds of things you're not really going to do with this. I'm just showing you that it's just a slide rule. It's a calculator that will do multiplication and division. It will not add and subtract. It can't add and subtract because on the number line, the units are of different length. They're logarithmic. So you can do multiplication and division, but you can't do addition and subtraction. You can do multiplication if you want to multiply some number, then you're going to use your 10 base. Let's say you want to multiply the number 11. Well, just put the 10 underneath the 11. Put the 10 underneath the 11. And what is 11 times 3? 11 times 3 is 33. 11 times 4 is 44. 11 times 12 is 132. 11 times 18 is 198. Right? You just set it up and then just go around and read your answers. Okay? Would you say that's quicker than a calculator?
It's pretty fast.
That's pretty fast, isn't it? Okay? It's for this reason right here that I was hoping one of you had an E6B because I was going to challenge you to a duel and I was going to show you how much faster I can calculate things with this than you can with that E6B. And when you're in an airplane, it's really important. And the reason that, everything else in life has become digitized, and calculators and computers, and everyone's got away from this type of stuff. But in the cockpit of an airplane, the reason these still exist and people still use them is because they are so much quicker and faster and easier to use than punching something in. I have it on my watch. I use it on my watch. I have an E6B right there on my watch. Right? They're just easier to use once you learn how to use them. So I want you to practice with it and learn how to use it. Okay. Now, that's enough of multiplication and division. Just know if you want to multiply or divide, you're going to use the 10 base. You want to multiply a number, put the 10 under where the number is, look around, find the number, and you find the answer right by it. The answer's right next. You want to divide, just set it up like that. And then look at the 10, and that's your answer. Okay? That's how you use it for that. You're virtually never going to use it for that reason. We're going to use it for these reasons: rate problems, air pressure and temperature problems, and wind correction problems. And these specifically come into play when you start getting into your cross-country phase. When you start working on your cross-countries, you're going to be doing all of these things. You calculate all of these things, okay? All right, so let's do a couple. Let's do a couple of these rate problems, so we're talking time. Remember, the outer ring is units, the middle ring is minutes, and the inner ring is hours. So go ahead and set your circular slide rule back up so everything lines up. 10 lines up with 10, 11 lines up with 11, and so forth. Just like that. It's hard for me to get it exact with my thumb here, but I'll try and get it as close as I can. So everything's lined up, okay? Or as close as you can get it lined up. The place I see the most errors that students make and pilots make, it's usually with younger pilots. It's usually with younger people that all you've had is calculators. If all you've had is calculators, then in your mind, if all you're used to is a calculator, in your mind, that's 3 different numbers, right? Does that represent 3 different numbers? Okay. Using a slide rule, that number can represent any of those. 6 can represent 60, 600, 6 billion, 6 trillion, 0.00000006. Does you understand what I'm saying? Okay. So when you're using a slide rule and you look at a number, when you look at this number, number 19, that number 19 can be 19. It can be 0.19. It could be 1.9. It could be 190. It could be a lot of different numbers, all right? So here's where you generally, if you're going to make a mistake using this thing, this is where you make it. You don't put the problem correctly in context in your head, and you look at the right number, but you don't put the decimal point in the right place. That's usually, if you're going to make a mistake, that's where you make the mistake, okay? So you have to, when you're using this, you really have to be thinking contextually about the problem and whether or not the answer that you're coming up with makes sense within the context of that problem. That's where the biggest problems come with these, okay? All right, so what I'm saying is you have to think. You can't just arbitrarily push a button and look at the answer. You have to use your brain a little bit, okay? All right. The light is darkest right underneath the lamp. That's right. One wise instructor, Yunjay, said that the other day. I thought, well, I'm going to figure out a way to use that. All right. Okay, so let's look at, so we've talked about the numbers. Let's look at the relationship between these A, B, and C scales. First of all, look at your B and C scales. I want you to understand that when you are using these A, B, and C scales for rate type problems, not when you're doing air pressure, temperature problems, or anything like that, but when you're doing rate type problems, which is probably 90% of what you do with this thing, okay? The B scale and the C scale, well, the A scale always represents units. It always represents units. The B scale always represents minutes, and the C scale always represents hours. And the way you can see that right away is that when you rotate the dial here, you'll notice that the B and the C stay together. Those numbers are always together. They don't change. Their relationship doesn't change. So I want you to look at the 12, for instance, right here. Look at the 12 on the B scale. What's the number on the C scale opposite it? 2 hours. 120 minutes is 2 hours. 210 minutes is 3 hours and 30 minutes. 300 minutes is 5 hours. You see where I'm going there? Okay. So when you're looking at the B and C scale, you're looking at minutes and hours. Anytime at all, if you're doing a problem and rate comes out of your mouth in any form, if you're talking rate in any form, and that's the kind of problem you're doing, B and C always represent minutes and hours. Okay. A always represents units. All right, so what do I mean by units? Okay. Miles per hour. If we're talking about miles per hour, then the units we're referring to are miles. If we're talking about gallons per hour, then the units represented out here are gallons. If we're talking about apples eaten, then the units out here represent apples. If we're talking about the number of bananas I can eat in an hour, the units out here are referring to bananas, right? If I'm talking about feet per minute, then the numbers out here, feet per hour, the numbers out here represent feet. So the units on this A scale represent what how many apples I'm eating an hour, how many oranges I'm eating an hour, how many statute miles per hour I'm going, how many nautical miles per hour I'm going, how many nautical miles, how many feet per hour I'm going, whatever that unit is, and make sure that you don't mix units. This is another area that I see errors on with students, new students. We have a tendency sometimes to be working in statute miles and nautical miles at the same time. Guess what? They're not the same thing. So you can't be working in the same thing. You can't say, hey, I went 25 nautical miles in 10 minutes, so let me see how many miles per hour I'm going. You can, but you have to do a conversion. So keep your units. If I say I can eat 5 apples in 1 hour, then I would move I'm just going to do this real quick. I would move my little 60 rate pointer to 5. That's how many apples I can eat in 1 hour. I can eat 5 apples in 1 hour. So for me to eat 15 apples, it's going to take me 180 minutes to eat 15 apples or whatever, 3 hours, right? But what I can't say is if I can eat 5 apples per hour, how many oranges can I eat in an hour? It's 2 different units. So make sure you keep your units the same. Don't mix oranges and apples. Okay, that's my little word of warning. All right, let's do a few of these. So set your E6B up again just so that it's in the neutral point or the starting point, just like this. And let's do a few of these. When we're doing time, speed, distance, we have 3 things that we're dealing with. What are they? Time, speed, and distance. Okay, we're doing time, speed, distance problems. We got 3 things: time, speed, distance. With this calculator, if we know 2 of them, this will tell us the third. Any 2. So sometimes you'll know these 2 and you get that one. Sometimes you'll know these 2, you get that one, right? So you just need to know 2. If you know your rate of speed, then you can calculate the distance if you know the time. If you know your rate of speed, you can calculate the time if you know the distance. All right, everybody tracking along with that? Okay, so let's do a couple where we know what our rate of speed is. Let's say that we're traveling at 110, and I'm not going to say miles per hour, knots per hour. I'm going to say units per hour, whatever those units are. We're traveling at 110 apples per hour. That's the speed. That's our rate. So we're using rate. So are we going to use the 10 index or the 60 index? So let's point to 60 at 110. That's the rate that we are traveling at. So we're going to point that at the only number on here that could represent 110. It's that one right there. Oh, I made that a little too big. This is the only number on this E6B that can represent 110, right there. So you're going to point your 60 at that. Okay. Remember how when we did the multiplication problem and we had to, and we were able to set it up and then just look around the dial? All right. If you're using a mechanical or not a mechanical, but an electronic E6B, and you have a speed of 110, you have to put in 110 rate, and then you have to put in, all right, how long is it going to take to go this far? And then you have to do another problem and put another one in and put another one in and put another one in. Here we don't. We're traveling at a rate of 110 units per hour. And if we go 20 units, it takes that long. 23 units, that long. If we go 60 units, that long. If we go 80 units, that long. 10 units, that long. 13 units, that long. 15 units, that long. Okay, so if we're doing 110 units per hour, how long is it going to take us to go 35 units? 35 is right here. Below it is what? So this is where you got to put the decimal point in the right place. So the number is 19. We're going 110 units per hour. And if we fly now for 35, what did I say? Yeah, 35 minutes, how many of those units are we going to cover? Would it be 190? No. Wouldn't be 190. If we're going 110 in 1 hour, How could we go 190 in a half an hour? If we're going 110, if we go 110 and we fly for 1 hour, how many are we going to cover? 110. If we go 110 and we fly for a half an hour, for 30 minutes, how many are we going to cover? Well, you go to your B ring, you go to your minutes, and you look outside to see the number of units. So if we're doing 110 for 35 minutes, we're going to go here to 35, and we're going to come out here. And we're going to cover 61, 2, 3, 4 miles. So just remember the relationship is this. Here's your relationship. This is always your units. This is minutes, and this is hours. And unless you're going long distances, you're probably not using the C ring. You're probably mainly using the A and the B ring, or the outer ring and the middle ring. All right? All right, let's say that let's say that we traveled a distance of, say we go a distance of 85 units. And I'm just going to use units because I want you to understand this is just a number, units. 85 units, and we do it in a time of 33 minutes. The question is, what is our speed? Okay, so remember, units is the A scale, minutes is the B scale. Set them opposite each other and look at your 60 index, and you've got your speed. So put minutes underneath units and look at 60. So 85 units in 33 minutes. I can't do this with my thumb. It just doesn't get exactly correct here. There we go. All right, so we got 85 units right here. 31, 2, 3 minutes right there. How fast are we going? About 154 units per hour. About 154 units per hour. Might be 154 statute miles per hour. Could be 154 nautical miles per hour. Could be 154 feet per hour. 154 millimeters per hour. 154 light years per hour. Whatever the unit is, that's how fast we're going. That's our rate at that point. Okay. Once we had that set up, if we're reasonably assured that that is our rate of speed, now we can just look around the dial and say, okay, if I'm going at that rate, and I got another 23 to go, it's going to take me just under 9 minutes. I got 80 to go, it's going to take me 31 minutes. So I've got another 120 to go, it's going to take me 46 minutes, 46 and a half minutes. So now I've got my circular slide rule, my E6B set up in the cockpit. I don't have to punch anything. I just look. Look at the number. That's how long it's going to take me. There's nothing going on in the cockpit now. I set it one time. Who used to say set it and forget it? Set it and forget it. Ron Popeil. Was that Ron Popeil? Set it and forget it. All right. All right, so let's do another one. Let's say that you're traveling, or let's see. Let's say that, let's say you're traveling at a rate of 105 units. 105 units. That's your rate, 105. And you want to go 350 of those units. 350 is the distance. How long is it going to take you? Your rate is 105. Remember, rate's your A scale. So when you think rate, you're thinking the triangle, the 60 triangle. Your rate is 105. So now make sure you point your rate index at the only number on that outer ring that can represent 105. Hint, it's not the 15. 15 doesn't represent 105. You got to find the only number that represents 105. Okay? And so this is where you should be set up, right here. Everybody got that? Everybody get it set there? Okay. Our distance is 350 miles. So again, this is the distance. So remember that outer ring, in other words, this is unit distances. This is still unit, the units. We're looking for the time now. So what's the only number on there that can represent 350? 3.5. This is the only number that can represent 350, right there. Okay, so now below it is a 20. All right, so what does 20 represent now? Excuse me, gave it away. What does 20 represent? Does that represent 20 minutes? Represents 200 minutes. So now you could go and look at the minute, the hours here, and you could see that that represents 3 hours, 3 hours and 20 minutes. Or you could divide 200 by 60 to get the same thing. Okay? All right? So if we're flying along at this rate of speed and our next checkpoint is 45 miles, how long is that going to take us to go another 45 miles? So our rate didn't change, so you don't have to spin anything. You just have to look around the dial. A distance of 45 miles is going to take how long?
4 hours.
No. No. We're going 45 miles. A little under 26 minutes. This is where you have the problem. You've got to make the problem make sense in your head. You can't just look at a number and assign some random, 260 to it or something like that. All right, you've got the problem you got to use your brain. You got to use your brain. You have to put the problem in context. Okay. All right. So we're traveling at this rate. We're still 105. So as we're flying along on our cross country, as we're going from checkpoint to checkpoint, and we're verifying our ground speed, we're verifying as we go that yep, our ground speed's still 105. Yep, still 105. Yep, still 105. And we're doing that by using the whiz wheel while we fly. And we know our next checkpoint then is, or let's say we don't want to use the next checkpoint. We want to, well, how long is it going to take us to go to this town over here? And we get our chart out and say, okay, well, that town is 15 miles from here. How long is it going to take us to get to that town? 15 miles away. Eight and a half minutes. It's going to take us 8.5 minutes to get that town. Right here, 15 miles, look below it, 8 minutes, 9 minutes, 8.5 minutes. Okay, that's how you use this. All right, so let's say we don't know what our ground speed is. We're just flying along. We're flying along, and we know based on where we are over the ground, there's a town here. We start a stopwatch, and there's another town up there, and we stop the stopwatch when we get to that town, and we get our chart out, and we know that the distance between those two towns was 35 miles. So our distance is 35, okay? And so is distance, is that an A, B, or a C thing? That's an A thing. So that distance is an A thing, all right? And we know that we had a time, we timed it. Let's say we timed it and it took us 7 minutes, okay? Is that an A, B, or a C thing? B, all right? So now what we're trying to find is what's the rate? What's the 60 rate? Is the 60 an A, B, or a C thing? Is this point up here? That's an A, right? Because we're looking at how many miles per hour or units per hour or whatever. Okay, so it took us 7 minutes to go 35 miles. How fast are we going? 7 minutes to go 35 miles. We're cooking. I'll tell you that. We're screaming through the sky. How fast are we going? 300. We're going 300. So 7 minutes to go 35, to go that far. So I'm going to put this guy on, what did I say? 7 minutes to go 35 miles. So 7 minutes, there's 35 right there. 7 is right there. And so our rate is 300 units. Okay? What if it took us, what if it had taken us, let's say it takes us, well, let's leave the 35, but instead of 7 minutes, it took us 15 minutes. It took us 15 minutes to go 35 miles. How fast are we going?
Okay, 40.
Everybody get 140? Okay. All right. So, I mean, that's how we do, this is how we do rate problems. All right. It's really pretty simple. I mean, it really is really super simple. If you'll just practice and do a few of these, you get it, you'll learn how to use it so fast. And it is so, and I promise you, it is faster than getting an electronic E6B and punching things in like a calculator. It takes up a lot less space in your flight bag. Doesn't take batteries. It's lightweight. If you have one like, who's got a metal one? I used to have a metal one. So these metal ones, when I started flying, when I would fly, they have these little lanyard on it. You hang this around your neck on a little lanyard. So you have it right there and it's just hanging right there while you fly. All right, I'm dating myself. Okay, so we're doing unit problems. Let's talk about gallons. That's a unit, right? That's something that we worry about. We worry about volume. So distance usually we're worried about. Sometimes we're worried about volume. What volume of fuel are we burning through in a certain amount of time? So if we know that our pilot operating handbook, let's say, says that we're burning at a particular power setting, let's say it says we're burning 15 gallons per hour. How would you start to set the problem up? What would you do? We have a rate of 15 gallons per hour. Where are you going to point the 60 index at? 15, that's our rate. The 60 index, and it says rate right on it. It says rate. If you know your rate, point that to the rate. If you don't know your rate, you've set it up the other way and you look at your rate to find your rate. So we're going to point the rate at 15. So now we're burning at a rate of 15 gallons per hour. So we're going to point the rate at 15. That's the rate of burn. If we were traveling at 15 miles per hour, that would be the rate of speed. But now it's the rate of burn, all right? And if we are then flying for 90 minutes, how much fuel are we going to burn through? Well, find the 90. See the 90? What's on the gallon side of that? 22.5. We're going to burn 22.5 gallons in 90 minutes. What if we flew for 100 minutes? 25 gallons. What if we flew for 35 minutes? 8.7 gallons. What if we flew for 1 hour? 15 gallons. 55 minutes, 13.75 gallons. Right? So once you set it, the beauty of this thing is once you set it up, you don't have to do any more, anything. It's set up, just look at it. Just find the number and look at it. And you have it, okay? All right. Let's say that you want to figure out what your burn rate is. And you fly, you know how much fuel you had when you took off. And you flew to some destination somewhere and you measure your fuel again and you burned, let's say, 22 gallons. You burned 22 gallons, okay? And the time it took you to burn those 22 gallons was 35 minutes. What's your rate of burn? It took you 35 minutes to burn 22 gallons. 35 minutes, remember minutes is here, and gallons is up here, right? Took you 35 minutes to burn, what did I say, 22 gallons? 35 minutes to burn 22 gallons. What is your rate of burn? 38 gallons per hour. That's how much fuel you're burning. 38 gallons per hour. Are we seeing how to use this thing? Is it hard?
Takes a little thought.
It takes a little thought. That's why we're going to go through a bunch of these problems, because I want you to learn how to use it. It's not hard. If you'll use it, it really is not hard. Once you just really start to grasp this relationship between these things here, and all I'm working on is this right now, because this is primarily what you're going to do. We're going to go through all of them, but this is what primarily we're doing when we do this. This and the wind side. So we're going to do a bunch here as well. But just remember that outer ring is units. It's apples, it's oranges, it's feet, it's statute miles or nautical miles or gallons or liters or quarts. It's units. It's units of something. The middle ring is always minutes when we're dealing with this. And the inner ring is the hours. Okay, so your units are on the outside and then minutes and hours on the inside. Rate is a 60-based problem, so anytime you're asking a question about time, how long did it take me to get there? How long is it going to take me to get there? How fast am I going? Those are all rate things. When we're dealing with rate things, we're dealing with the 60. It says rate right on it. And once the problem is set up, that will be pointing at the rate, whatever the rate is. Speed, apples you eat per hour, gallons you burn per hour, whatever that rate is, that will be pointing at that. So if you know what the rate is, you point it there first. If you don't, you set the other relationship up and look at what the rate is. Okay? All right. Let's say that you're burning 5.5 gallons per hour and you fly for 5 minutes. How many gallons are you going to burn in 5 minutes, burning 5.5 gallons per hour? Now you really got to put the decimal point in the right place here. You're burning at a rate of 5.5 gallons per hour. 5.5, you're burning, your rate of burn, your gallons per hour equals 5.5, and you fly for 5 minutes. How much fuel have you burned? 5.5 gallons per hour for 5 minutes.
What?
0.46. 0.46 gallons. All right, so let's set it up here. So our rate is 55. That's it. 55 is the only number that can represent 5.5, right? So let's point the 60 index at 55. That is our rate. That's the rate at which we're eating apples, the rate at which we're flying through the air, the rate at which we're burning gas, the rate at which we're whatever. That's our rate of units that we're burning off. We are traveling at 5 minutes, right here. That's the only number that can represent 5. We look outside of that, we get 46 or so, all right? About 46, let's call it 46. So does 46 in the context of this problem represent 46 gallons? Can't. It can't, right? Could it represent 4.6 gallons? No, it can't. We're burning 5.5 in an hour. We're only flying for 5 minutes. So this is where you got to use your brain. So it represents 0.46 gallons. So you got to move that decimal point one direction or another until the problem makes sense. Okay? That's if there's a drawback to a slide rule, that's it. You have to use your brain. Okay? All right. So we're burning this rate. We fly for 3.5 hours. How much fuel are we going to burn? Find 3.5 hours on here. So now you could go to the 3.5 right here. Right? 3.5 hours. How much fuel are we going to burn? 19.2. 19.2 gallons in 3.5 hours. All right. What is 17 divided by 15? What's 17 divided by 15? Use the 10 scale. Remember I showed you how to do division on it. 17 divided by 15 is what? 1.13. There you go, 1.13. 17, oh, you weren't here in the beginning. So we have a 60 rate and we have a 10 rate. If you set up a problem, 17 divided by 15. So put the 15, spin the 15 under the 17 and look at the 10. There's your answer. Okay. All right. Let's talk. I'm going to come back. We're going to come back and do some of these in a minute, but I want to start moving into air pressure and temperature stuff right now before we take the break. I want to talk about it a little bit, and then we'll do some of the problems. So, for those of you who've been in my classes before, how often do I talk about pressure and temperature? Just about every single class, don't I? Pressure and temperature, because it is part and parcel to understanding aviation, understanding performance, and all things about the airplane, how it flies, how it performs, all that kind of stuff, right? Pressure and temperature. So you know that we start with the International Standard Atmosphere, and tell me what that is. Tell me what the pressure is. What's the temperature? And where does that exist on a standard day? On a standard day. You're right, but on a standard day, where does that exist? Sea level, yeah. It exists somewhere. It exists somewhere, but usually not at sea level. Okay. All right, so because it typically usually does not exist at sea level, that means that when we do problems that require us to take into account for pressure and temperature, we have to have a means of taking into account for pressure and temperature, okay? And the problems and the things that we're typically looking for when we're doing those problems are, we're trying to figure out true airspeed, or we're trying to figure out true altitude, or we're trying to figure out density altitude. So anytime we need to figure out what is our true airspeed, we have to account for pressure and temperature. Anytime we want to figure out what is the true altitude, we have to account for pressure and temperature. Anytime we want to figure out what is the density altitude, we have to know the pressure and the temperature. And by knowing those two things, we can calculate these things. So this computer does that for us. All right, so I'm going to show you how that works. So put your computer back into a state of 0, if you will. Everything back at 0. And I want to point out some other parts. So we've looked at the outer ring, the middle ring, and the inner ring. And the one thing I didn't do, and maybe I'll talk about this real quick before the break. Notice around the outside of the E6B, right up next to the 10, you see oil pounds. You see going to the right imperial gallons, kilometers, U.S. gallons, feet, fuel, and so forth. It has some different things all the way around. On the inside has some of the other things. This is how you can do conversions. You can do conversions here, as an example. You're not likely to do this. You're just not likely to do this very often, but I'll show you how you do it if you want to do it. Let's say you wanted to convert. You want to know the difference between imperial gallons and U.S. gallons, as an example. So if you can see U.S. gallons here, you see U.S. gallons down here, imperial gallons. Well, if you want the outer ring to represent imperial gallons and the inner ring to represent U.S. gallons, put the U.S. gallon arrow underneath the imperial gallon arrow. Go ahead and do that. Spin this so that the U.S. gallon arrow is under imperial gallon arrow. And once you understand this, you can do it with any of the other units. So we're going to spin this so U.S. gallons is under imperial gallons right there. So you see that? I could have done it the other way. So imperial gallons is opposite U.S. gallons right here. I could have done it where I took imperial gallons over here and moved it over to U.S. gallons over here. Then it just would have been, the units would have been on the other side of the scale. So it doesn't matter which way you do it. All right. Now, what this is showing us is that 1 imperial gallon is 1.2 U.S. gallons. 14 imperial gallons is 16.8 U.S. gallons. 21 imperial gallons is 25.2 U.S. gallons. That's all. It just gives us a ratio of the of the conversion. Okay, that's what all these other numbers around here mean. So let's do speed real quick. The best way to do speed, you could do the same thing here, but the best way to do it is if you look over here, and this one you'll use in getting your units correct. So if you're working between, let's say, statute miles per hour or nautical miles per hour, if you look over here to the upper left, you'll see this arrow right here. You see right here, you see that? It says nautical with an arrow here and statute with an arrow there. Everybody see that? Okay. If you're trying to do a conversion of a particular speed, let's say you want to know how many, let's say you know that your airspeed indicator reads in miles per hour like ours does. And you want to know, hey, if I'm reading 110 miles per hour, how many nautical miles per hour is that? That's a good realistic example. Well, so if we're going 110 statute miles per hour, take that 110 and spin it till it's under the statute arrow and then read the nautical side. And that'll give you your conversion.
Does it have to be set at 0?
No. So here, I'll set it up here. So if we're doing 110, I'll put the 11. If we're doing 110 statute, I'll put it right there. So if we're doing 110 statute, then we're going 96 nautical miles per hour. So that's the conversion. If you were doing 110 nautical, you would spin the 11 over here to nautical and you could come back here and read statute. Okay? So these, usually when you see these things around here, that's what's happening. If you want to do the conversion of, let's see, where's it at on here? Thought I saw it on there. There we go, statute.
That's 95 nautical.
That's 96, yeah, or whatever it is, right? So that's a way to do convert. I don't want to spend too much time on conversions because you're probably not going to use those. But that's what all these other things are: imperial gallons, kilometers. Well, here's another one too. You could also, when you're set up like this, as an example, I'll show you. As you're set up like this, if you're doing 110 statute miles per hour, that means you're going 96 nautical miles per hour. You can look over here and you can see that you're going 178 kilometers per hour. That sets up right there. There's your kilometers per hour. So when these are set here, you're reading your kilometers over here, if you care. I mean, those aren't units you're likely to be switching back and forth between. But this is nautical to statute. That's a conversion that you'll frequently do in flying. You'll frequently do that conversion, so know how to do that. All right, go ahead and set this. I forgot to talk to you about that before, that's why I wanted to bring it up. Go ahead and set this back to the quote-unquote 0 state, or the standard state, and I want to show you something. I want to show you these boxes in here and what these mean. Okay. Notice that this one says, notice this set of directions right here says airspeed correction. This one over here says altitude correction. Okay? So this one says airspeed correction. This one says altitude correction.
This was on the written test.
Okay? And up here, this says density altitude. See that? That's what this set of directions goes with that set of numbers. This set of directions goes with that set of numbers. Okay? First off, just get that through your head how these work, okay? All right? Who hasn't taken your written yet? Okay. Wow, a bunch of you. All right. You can take this in with you. You can take this E6B with you. And the directions are written on it. They're printed on there. I don't know that you can take the, if you take an electronic E6B, I'm not sure you can take the directions in with you. You have to know how to use it, I think. I might be wrong on that. But this, the directions are printed all over it, so you can take it with you. All right, just wanted to point that out. Okay, so let me show you a few things. When this is set up in its zero, quote unquote, zero or standard condition, I want you to take notice of something. You can look at either one of these boxes. First of all, look here, and what does this say right here? What's it say there? Pressure in thousands of feet, and what's it say up here? Temperature in Celsius. So we've got pressure, and we've got temperature in Celsius, okay? We've got it on both sides. So the bottom set of numbers here, this set of numbers right here is representing pressure, altitude. This set of numbers over here is representing pressure, altitude. This set of numbers up here is representing temperature. This set of numbers up here is representing temperature. Got that? See that? Pretty easy to understand. Understand that the altitude, the pressure altitude is in thousands of feet. Thousands of feet. Don't make that mistake. That's a mistake I see made too. So when I'm looking at this 5 right here, what's that represent? 5,000 feet. When I look at this 20 right here, what's that represent? 20,000 feet. Okay, so that's in feet. The temperature line is in Celsius. Okay. All right, I want you to look at, you could look at either one, and I'll show it to you in either one. But this is set up for from as far as an atmospheric pressure and temperature standpoint, this is set up for standard. So what's the temperature at sea level on a standard day? Okay, look at these, look at here, look at here, and look at the relationship between zero altitude and temperature, and what's it set to on both windows. So if I find zero altitude here and I look above it, what temperature is that represented at right there? 15 degrees Celsius. If I go over here and I look at zero and I look above it, what temperature is that? Well, there's 0, 10, 15 degrees Celsius. So when it's in this state, my pressure altitude windows all go to 0, all go to a standard day. At sea level, the temperature is 15 degrees Celsius. If I'm at sea level on a standard day, what's the density altitude? 0. Density altitude is 0. Reads 0. So we're at a standard condition right here, the way it's set up when it's standard. Everybody see that? Okay. So if you forget what temperature and if you forget what the temperature should be on a standard day, you could do this with your E6B and read it right there. Right? Line everything up and read it. 15 degrees. Okay. So when we apply pressure and temperature variation to the standard, we can read, this thing will tell us what is our true airspeed, what is our true altitude, or what is our density altitude, depending on how the way we set this up and what we're trying to find. So let's do just one real quick. First of all, what happens with true airspeed as the density of the air decreases? You can look there if you need to. What happens to this as that goes down? That one goes up. So what happens to true airspeed as density decreases? It goes up. We go faster. The thinner the air, the faster we go. All right? So on a standard day, okay, in standard conditions, our airspeed at sea level, if we were doing, let's say, 170, we'd be doing 170. These numbers all line up, all right? Let's read right here. The way we're going to do this airspeed correction, we're going to set our pressure altitude opposite Celsius in the window, this window. If we're doing airspeed correction, we're using this set of windows right here, okay? This side goes with this side. So pressure altitude opposite degrees Celsius. So let's say that we're flying at a pressure altitude of 6,000 feet. And up there at that pressure altitude, we look at our air temperature gauge, our outside air temperature gauge, and it reads, let's say it reads 5 degrees Celsius. Okay, let's say that's what it reads. So we're at 6,000 foot pressure altitude at 5 degrees Celsius. So what do we want to do? We want to set our pressure altitude opposite Celsius in the window. So do that. Set 6,000 feet, which is right here. That's 6,000 feet right there. Set that opposite +5, which is right here. Put those two numbers together. So 6,000 feet and +5. This isn't much of a change here because if we go up to 6,000 feet, the temperature should be somewhere close to +5. It should be somewhere in that neighborhood. But what we're going to find here, now when we read the directions, what's it say? Opposite calibrated airspeed on inner scale, read true airspeed on outer scale. All right, so what is calibrated airspeed referring to here? We have to do a little quick airspeed review. We have indicated airspeed, which is what? What it shows, what the airspeed indicator shows, based on the, the pitot-static system, the pitot tube sticking out, static port, all that. All right, so we get an airspeed indication. Okay, airspeed indication is this right here. This is what our airspeed indicator is reading. That right there, it's reading pressure times static air pressure times the velocity. That's dynamic pressure. Okay, what is, and then we go from indicated airspeed to calibrated airspeed. What is calibrated airspeed? Calibrated airspeed is indicated airspeed corrected for some errors in the system. Installation error and position error. So if we are flying along, let's say, here's my pitot tube sticking out of the wing. If I'm flying along like this, you can picture the airflow going in probably in a pretty good way, but if I'm flying slower at a higher angle of attack, I'm going to get some error introduced into the system, right? So as I fly slower, there's a bigger difference between indicated airspeed and calibrated airspeed. But generally speaking, when we're cruising along, are we cruising along like this, or are we cruising along like that? Once we're up flying, we're going to Florida. We're going to go like this, we're going to go like that. Okay, so because we're traveling at a faster speed, our pitot tube is down into the wind, we're getting better airflow into the pitot tube. The difference, we say in small GA airplanes, the difference between calibrated airspeed and indicated airspeed is nil, is negligible, so we don't apply any factor to it. All right? So in this case, my calibrated airspeed is my indicated airspeed. They're close enough to the same that we're not going to get a chart out and find, oh, it's 1 knot off. I don't care, right? It's close enough that we're not going to try and split gnat's hairs over it. Okay, so now I look at my airspeed indicator. This is my situation. My pressure altitude 6,000 feet. The temperature outside is +5. I set this up so that I have 6,000 feet opposite +5 right there. Now I read my inner scale. I read my calibrated airspeed. So if my indicated airspeed now reads, let's say 120, I want to find 120 right here. And on the outer scale, read your true airspeed. So my true airspeed is 131. My true airspeed is 131. Does that make sense? The thinner the air, the faster we move through it, per that equation right there, right? The thinner the air, the faster we move through it. Let's say that my pressure altitude is 10,000 feet and the temperature is still 5 degrees Celsius. But we're 10,000 feet and the temperature hasn't changed. It's 5 degrees Celsius at 10,000 feet. Now what's happened? So now we have 10,000 feet here opposite 5 degrees Celsius. Here's my indicated airspeed right here. What's my true airspeed? 142. Notice that my indicated airspeed didn't change, but my true airspeed changed, right? Because of that relationship in that equation right there. So the thinner the air becomes, the faster we have to physically move through it. That's the concept of true airspeed. We have to move faster through it. The other thing that we can see now, because at 10,000 feet, the temperature should be quite a bit colder than 5 degrees Celsius. That's pretty warm for 10,000 feet. So what's that do to our density altitude? What's our density altitude in this scenario? 11,000 feet, okay? So we're at 11,000 foot density altitude. So our density altitude, so our aircraft, and again, this is not terrible, really, but it's not terrible in this case, but our aircraft is going to perform as though it's at 11,000 feet, not 10,000 feet.
You know, there are times I've kind of watched that on the 404 flight. Our days here, sometimes we're like at 2,500 feet.
Sure.
The altitude.
Sure, absolutely.
And I noticed on one of those days, I wasn't climbing as well.
No,
as when it was more like closer to sea level.
That's exactly right. That's exactly right.
Yeah,
You get
that's just a notice that I
absolutely.
Oh, gosh,
So
I'm not climbing
so
here.
for those of you who started flying, let's say through the fall, winter, if you haven't flown into the dead of in the 100-degree temperatures, you're going to notice a big change in the way the aircraft performs. The aircraft performs way differently in July than it does in January. Way differently, okay? And it's because of this. It's because the air is thinner. So the aircraft the density altitude is higher. And all the aircraft cares about is density altitude. It does not care one iota how many feet we are above sea level. It does not care. It only cares about what is the relative thickness of the air, what is the density of the air, the parcel of air that we're flying in. That's how it performs. All right, let's take a break. And if you didn't sign in. Please eat those donuts, all of them. Okay, let's get started again. So we're going to go back to, again, this airspeed correction problem, because this is one that you'll use, right, quite a bit. One thing, when you come to me for a stage 2 check or a stage 3 check or whatever, when I'm looking at your cross-country flight planning, I'm going to tell you the first place I look. The first thing I do is I look at that box in the speed column that says calibrated airspeed on top there, and then below it is true airspeed. So we start with our calibrated airspeed, which means what? True airspeed, indicated airspeed, right? And then I look at your true airspeed numbers below it. And how often do you think I see that the calibrated airspeed and the true airspeed are the same? And guess what that tells me? It's wrong. Or I see a calibrated airspeed and a true airspeed that's slower than the calibrated airspeed. Guess what? It's wrong. Okay, because you're not understanding this. So that's a first place I'll look, because I see that error a lot. So let's talk more about that and understand that.
Thank you for that.
What's that? You're welcome. You're welcome. Just make sure those are right. Well, the other thing I'll see is this. I see units mixing a lot. Okay, so our airspeed indicators are calibrated in what units? Miles per hour. What do we typically use in aviation? Knots, okay? So my suggestion is to convert everything to knots. But if you don't want to, that's okay too. But if I see 110 miles per hour calibrated airspeed, and then I see, 100 true airspeed, first thing I'll think is, well, it's probably wrong, but then I'll ask the question, well, is this true airspeed? Is this knots or miles per hour? And they'll point down here, they'll say that's knots, and then I know they didn't do the conversion. And so now how many miles is this? So that's 10 miles statute or whatever, and I'll realize they're using two different units. So you're measuring in statute miles on the chart, and you're calculating in nautical miles per hour. And so you got apples over here, you got oranges over here. Guess what's going to be? It ain't going to work, right? Just make sure you get your units correct. Keep your units correct. All right, let's go back to this so that we can use this to really get a better understanding and just really grasp this concept of true airspeed. So let's assume that our indicated airspeed is 100, because that's an easy one just to follow around the dial. Okay, if our indicated airspeed is 100 and our let's say our altitude we're flying at is 5,000, and we're just going to keep the temperature at 0 just to make this easy. We're just going to look at pressure difference. I'm not going to vary the temperature. So let's say we're flying at 5,000 feet. Well, first, let's say we're flying at sea level. We have a 0, let's say 0 temperature at 0 altitude. So put 0 and 0 opposite there. I'm going to keep the temperature at 0. Okay? If this were the case, if the temperature was 0 and we're at sea level, okay, the pressure altitude is 0, all right, and we're flying with an indicated airspeed of 100. Now this is a case where it's backwards. What's our true airspeed? 91. It's 91 because we're actually colder than standard. The air is actually denser than standard pressure. Usually that doesn't happen. Usually it'll go, sometimes it does. Middle of winter it could do that. But usually when we're going up, it's going to get thinner, right? So now let's say we go from 0 altitude. We're going to keep the temperature at 0, but we go from a 0 altitude to 3,000 feet. So I'll just spin this to go to 3,000 foot pressure altitude. 3,000 foot pressure altitude right there. Okay, so we have still 0 temperature, but now we're at a 3,000 foot pressure altitude. So we've gotten up where the air got thinner. What happened to our airspeed? Our true airspeed started moving up. The air's thinner. That relationship is working. As the pressure decreases, the velocity has to go up. Okay, let's go up to 6,000 feet. Well, again, we're just going to keep the temperature where it's at. We'll keep it at 0, although we know that doesn't actually happen, right? Now we go up to 6,000 feet. What happened to our true airspeed? Got even faster. Yeah. Let's go up to 10,000 feet. What happened to our true airspeed? Got even higher. So you can see this relationship here. This relationship between our indicated airspeed and our true airspeed on this outer scale. As the air gets thinner, that relationship and that equation has to hold true. It's got to hold true. So generally speaking, the higher we go, the faster we go. This is why one of the reasons that we try to fly at higher altitudes, because we take advantage of free airspeed. We're going faster up there. Now, wind can throw a giant wrench in that, which we're going to talk about next when we get to wind correction here in a minute. But our true airspeed is truly faster. The speed that we're moving through the parcel of air is faster, our true airspeed, okay? And then now let's put temperature into it. So let's say we're at 10,000 feet, the temperature's 0. You can see our true airspeed at 100 would be about 100, what would that be, 118? Well, what if the temperature was 10 degrees Celsius up there? So quite a bit hotter. So now 10,000 feet with 10 degrees Celsius. Let's see how temperature affects things. What happened to your true airspeed? It got higher. So lower density air, in other words, higher altitude, higher true airspeed. Higher temperature, higher airspeed. Because temperature, what does increased temperature do to density of air? Decreases it. So it makes sense. If it's hot, your true airspeed is going to be faster. If the air is less dense, your true airspeed is going to be faster. If the air is less dense and it's hot, it's going to be faster. So as we get hot air, less dense air, we go faster. And that also equates to poor performance. The only performance metric that goes up with density altitude, with decrease in pressure and increase in temperature, the only performance metric that gets better is our airspeed. And it's because that gets better that so many other things get worse. If our true airspeed is faster, we need longer runways to take off. We need longer runways to land because we're truly going faster. So we need longer runways as an example. All right? Our engine performance is decreased because if it's a normally aspirated engine, normally aspirated meaning that it breathes on its own just like we do. We don't have a supercharger or turbocharger. It doesn't have oxygen, supplemental oxygen going in there. As you get higher climbing the mountain, it's harder to climb the mountain. You don't have the oxygen. The higher the normally aspirated engine, normally aspirated meaning it doesn't have a supercharger, it's using outside air pressure. The higher we go, the less power it can develop, just like us climbing a mountain. The less power we don't have as much oxygen, right? So performance degrades. So the only thing that gets better up there, and there's a point where it don't get any better, obviously, because it's normally aspirated, is the true airspeed. All right, so you can use this to kind of visualize this relationship between pressure and temperature and what it does to our speeds and how our speeds increase as we get up there in altitude. All right, now let's look at true altitude as opposed to true airspeed.
Would that hold true to even at higher altitude, even like a jet engine? Or
So
not
jet,
gonna climb to something?
well, no, because those are not normally aspirated. The jet engine itself pressurizes the air. The turbine engine pressurizes the air.
Yeah, but the density of the air is not gonna allow you, like your density altitude is not gonna perform the same.
Okay, but the sheer power, the sheer thrust, the amount of thrust that you can get out of those engines. In other words, if you look at a power curve for a piston engine, especially a normally aspirated engine, and you look at, and it's going to do something like this. It's going to bleed off with speed and so forth. A jet engine's power curve looks like this. It's a straight line. It's just a straight line. Okay, so it can develop the thrust and the power that it needs, and it's not normally aspirated, as an example. So the pressure, sea level pressure, let's say is 2992. If I take off, if I have 20, let's say I have 30 inches of manifold pressure that I'm reading in the engine from a power gauge standpoint. I got 30 inches of manifold pressure on a normally aspirated engine. I put full power in, I read 30 inches of pressure. What that's telling me is at the intake manifold, going into the engine, at the intake manifold, just before the fuel and air go to the cylinders, at that intake manifold, I'm reading 30 inches of pressure. As I climb, what do you think happens to that pressure reading? It goes down. So I'm not able to put as much potential power into the engine. But if I have a supercharger or turbocharger, I can repressurize it and keep 30 inches all the way up as I climb. So I can get sea level climb performance, even at higher altitudes, because I'm pressurizing the air that I'm sending to the engine. It's like you climbing Mount Everest with an oxygen tank. You can just keep on going. You got oxygen being forced in. So that's the difference between a normally aspirated engine and a turbocharged or supercharged. And when you get a jet, that is compressing that air that's going to the combustion chamber. So you don't get that loss of power. Okay? And now because of that, they can take advantage of not going to 10,000. Well, here, let me give you an example. Let's take this guy, spin this guy up to using the true airspeed one here. Let's say let's keep it at 0 and just take it up to 35,000 feet. Take it to 35,000 feet. You go to 35,000 feet, if you're indicating 100, you're doing 210 or 220. You're doubling your speed. So you get on a jet. You guys, when you're on whatever, you get the little app that shows the ground speed from. What's the ground speed typically running when they're up there 35, 40,000 feet? What's your ground speed showing? 500 miles per hour, 500 knots, however they have it reading. Do you think that's what they're seeing on their airspeed indicator? No. No. They're seeing, if you're seeing 500 knots, they're seeing 260, 70 knots, 80 knots. They're seeing this, you're seeing that. Their indicated airspeed, this number, is 250. But that number is 500. Right? That's what you're seeing. That's what's happening there.
All related to pressure.
All related to pressure and temperature. All related to pressure and temperature. Okay? All right. Let's go, Let's look at the other side now. Let's look at the altitude side of the deal here. So we've been working on airspeed correction. So airspeed correction, you have to take into account pressure and temperature. You got to take into account pressure and temperature. Altitude, you have to do the same thing. So let's do a real quick review on altitudes. We got a bunch of different types of altitudes. We just talked about one. We talked about density altitude, but let's talk about the other ones. We have true altitude. What is true altitude?
What altitude you're actually at?
Actually at above what?
Sea level.
Sea level. True altitude is height above sea level. What is absolute altitude? Height above ground level. Okay. Then we have pressure altitude. We have indicated altitude, which is whatever the altimeter indicates, and that'll depend on how we have it set. But we have pressure altitude, which we're talking about here. What is pressure altitude? Maybe. Where's pressure altitude? Remember, every time we talk about altitude, what we're saying is, how high are we above something? No. How high are we above something? If I'm saying absolute altitude, then I'm saying how high am I above the ground? If I'm saying true altitude, I'm measuring how high I am above sea level. If I'm measuring density altitude, I'm saying what altitude does the density of the air, what is the density altitude of air based on a standard day, is what I'm saying. If I'm saying what is pressure altitude, I'm asking how high am I above the standard datum plane? Remember, what's the standard datum plane? No?
On a standard day.
On a standard day, it's sea level. 29.92 is the standard datum plane. So wherever 29.92 exists in the atmosphere, pressure altitude is how high am I above that. So if it's a standard day and this is sea level, then 29.92 exists here. But what if it gets real hot that in the morning it's here? Maybe now it's real hot and the air got lighter, right? 29.92 moved around in the atmosphere. So wherever 29.92 is, how high am I above that? That determines pressure altitude. How can we get pressure altitude? How do we know what the pressure altitude is? There's two ways that we can get the pressure altitude. What's one of them? What's the easiest? What's the one that involves no math? No, that doesn't give us pressure altitude. You set your altimeter to 29.92 and read it. Because when you set your altimeter to 29.92, what you're saying is, tell me how high I am above 29.92. And 29.92 is the standard datum plane. So now your altimeter will say, this is how high you are above this pressure level. So that's the easiest method of finding pressure altitude. The other method is to calculate the pressure altitude based on ATIS, based on an altimeter setting. And the way you're going to do that is you're going to take 29.92 and you're going to subtract whatever the current setting is. Whatever the current altimeter setting is. Then you're going to multiply that times 1,000. And then you're going to add your indicated altitude. And that will give you pressure altitude. You could do it that way, or you could set your altimeter to 29.92 and read it. Which one do you prefer? Whichever one you want. Doesn't matter. Doesn't make any difference. The point is, pressure altitude is the altitude that we're referring to when we're talking about these pressure-related issues. We're talking about pressure altitude, not true altitude. All right. When you fly, somebody give me the altimeter setting for here right now. Somebody look at ATIS and tell me what the altimeter setting is right now, right here. 29.83. All right, so 29.83. So I'm going to say, let's say that this is sea level right here. And this is our airport up here at, we're just going to say it's 650 feet. I know it's like 658 somewhere on airport property. Let's call it 650 feet. If we're sitting in our airplane right here, and we put in our altimeter 29.83, what should our altimeter read? 650. Therefore, where does a pressure level of 29.83 exist? Sea level. Down here is 29.83, because when we put it in our altimeter, it says we're 650 feet above that pressure level. So when we get an altimeter setting, when you hear an altimeter setting, what they're saying is the pressure level, the pressure at sea level is this. So right here, right now in New Braunfels, at the New Braunfels Airport, if we were to dig a hole 650 feet down and lower a barometer down into it, it should read 29.83. And when we put 29.83 in our altimeter should say we are 650 feet above that pressure level, which exists at sea level. Does this make sense? We do this because in aviation, 99% of the time we fly, what do we want our altimeter to be giving us? What kind of altitude do we want our altimeter to be reading back to us? True altitude, sea level, height above sea level. We want, most of the time, when we're looking at, when we read an indicated altitude, an altitude indicated on our altimeter, what we want it to be reading is true altitude. How high am I above sea level? That's what we want it to be. However, what affects the reading? What can make that error? What can make it wrong? Incorrect pressure and incorrect temperature. So we need a way of correcting what we see to get true altitude or closer to true altitude than what our altimeter reads. That's all we're doing, okay? Does it matter so much when we're flying around Texas? If we're flying at 5,000 feet and you keep your altimeter set to the current reading as you fly along, you fly along, you fly along, you keep adjusting it so that it's adjusting and doing the correct thing, and you're out over Texas, and you're flying at a cruising altitude of 5,000 feet indicated on your altimeter. Do you really care whether the pressure and temperature is off and it's not really 5,000 feet? Maybe it's 5,200 feet, maybe it's 4,800 feet. Do you care that much? What if you're out over Colorado?
You should.
Now you're going to care a little bit more. Now you really maybe want to adjust your altimeter for the actual pressure and temperature where you're flying, and not just what they say it is 8,000, 10,000 feet below you. That's what we do over here. This is a correction for altitude. This is what we do over here. And we're going to do the same thing. We're going to correct for pressure and temperature. So let's say that let's just read the directions. We're going to set the pressure altitude opposite the Celsius, just like we did over here, right? And then we're going to opposite our calibrated altitude on this B scale, we're going to read our true altitude on the outer scale. What is our, in this case, what are we referring to when we say calibrated altitude here? Because that's not an altitude I typically use. It's what we're indicating, yeah. By calibrated, what we're saying is, hey, we took off over here at New Braunfels and they said 2983. So we took off and we climbed up to 10,000 feet and our altimeter is still, set to 2983. So our altimeter is reading 10,000 feet when we got up here. But that's what's indicated. That's what's calibrated based on what it says it's supposed to be at sea level, which it's probably not exactly, but it's going to be pretty close, right? But we want to know what is our, let's correct it and get closer to true altitude. This is supposed to be representing true altitude, but it's probably not. Because when we went from here to here, the pressure didn't decrease at 1 inch per 1,000 feet like it does on a standard day. The temperature didn't decrease by 2 degrees Celsius per 1,000 feet like it does on a standard day. We have irregularities in the atmosphere we have to account for. This is where we account for them, right here. So let's do that. Let's say that we are up at, so we get up to 10,000 feet. How are we going to know what the pressure altitude is up there? We're going to change our altimeter setting to 29.92. We're going to read it. That's our pressure altitude. Then we set it back to 2983. Right? So we get our pressure. So let's say we get up there we'll just use 10,000 for purposes of this. No, let's not. Let's say, yeah, we use 10,000. Let's say we get up there and the temperature at 10,000 feet is 15 degrees Celsius. Is that higher than standard or lower than standard?
Higher.
It's higher than standard, quite a bit higher than standard because it should be -5 up there, right? So it's 20 degrees higher than standard. So is that going to have an effect on the altitude? It sure is. So let's see how much of an effect it has. So let's put 10,000 feet right here, opposite 15 degrees Celsius right there. So we're going to move 10,000 feet opposite 15 degrees Celsius. Okay, let me get the red markers, you can see better. So we've got 10,000 feet right here, opposite 15 degrees Celsius right there. Everybody see that? Okay. We're flying at an indicated altitude of 10,000 feet. What's our true altitude? 10,007 or 800, yeah, right here. So we're quite a bit higher. We're quite a bit higher than what our altimeter is reading because the temperature is so high, right? You heard that adage, hot to cold, look out below, high to low, look out below. So I'm going to show you the relationship right here now with that, okay? We just did the opposite relationship to that. Hot to cold, look out below. So what would a temperature be at 10,000 feet that's colder than standard? What should the temperature be at 10,000 feet on a standard day? How much? -5. -5. What if it's -20? What if it were -20 up there at 10,000 feet? So it's colder than standard. Remember, hot to cold, look out below. It's colder than standard. So 10,000 feet opposite -20.
You'd be at less altitude.
That's right. That's exactly right. So that's the saying put visually in practice. In that case, if that were the temperature up there, you're indicating 10,000 feet, but you're actually at 9,500 feet. That's an example of hot to cold, look out below. Your altimeter is reading higher than your actual altitude. Okay? Hot to cold, look out below.
It's good to work.
Okay? All right. So to correct for altitude, we're doing the same thing we do over here. It's pressure and temperature. It's pressure and temperature. And then you just read your scales. What you're indicated and what's actually happening, what's your true. What's your indicated airspeed, what's your true airspeed. What's your indicated altitude, what's your true altitude. Okay? So the inner scale, another way to think about when we're doing these, the inner scale, the B scale, is calibrated or indicated. And the A scale is true. When you're doing these kind of problems, your B scale is your calibrated number or your indicated number, and your outer scale is your true number, true altitude or true airspeed. When you're doing those, you don't have to remember this. You don't have to remember these. You can read them. You can read it. The directions, it's right there. You don't have to remember it. It's right there. Okay? All right, so let me give you a problem here. Let's say that you're at a, let's say your indicated altitude, let's say your pressure altitude, and for purposes of making this easy, I'm going to make it harder in the next hour, I promise you. I'm going to make it harder, but for purposes of making it easier right here, you're going to use the same indicated altitude. You're going to assume indicated altitude and pressure altitude are the same. We're just going to adjust for temperature, okay? So let's say we're at an indicated / pressure altitude of 6,000 feet. And the temperature is 15 degrees Celsius. What's your true altitude?
15 degrees Celsius.
15 Celsius, 6,000 feet. What's your true altitude?
It's 10,700. You're saying 10,000 feet?
6,000 feet.
6,000.
Yeah. Isn't that what I said? Did I say? I didn't write it down. Did I say that? 6,000 and...
6,000 at 15.
At 15, okay, 6,000 at 15 degrees. Okay. What's your true altitude?
6,250.
So if you're, so we got it set up with 6,000 feet here, right? At 15, oh, I got it in the wrong place. Hold on. I set up wrong. 6,000 feet at 15 is right there.
Positive 15, not negative 15.
Thank you. Thank you. 6,000 feet at 15, right there. Oops. Yeah, right there, close enough. And if we're at a indicated altitude of 6,000, we're at a true altitude of 6250, yeah, something like that. About 250 feet difference in true altitude, all because of temperature. Does that make sense? Okay. All right. Okay. What's 27 divided by 5? What's 27 divided by 5?
Uh,
27 divided by 5. Yeah. 5.4 ish. Yeah. Everybody see that? Okay. All right. What's 36 times 45? Hmm? 36 times, what's it, 45? Times.
36 times.
Is that what I said? 36 times 45? Yes, I said 36 times 45.
795 approximately.
No.
No?
36 times 45. So you're going to put the 10 under the 36 and then find the 45 and look below it. You're just doing the multiplication problem backwards. I mean, the division problem backwards, so you do. Thirty-six times 45. The number is 125. Now put the decimal point where it needs to be. That'd be 1250, I think, right? See that? I'm just throwing those in there because I want you to understand the relationship between the numbers here is all. You're not going to do multiplication division problems typically with these. I just want you to understand this relationship. Okay. If I'm traveling at 160 units per hour and I'm going 380 units, how long is it going to take me? 160 units per hour, I'm going 380 of those units. How long will that take? 160 units per hour, that's my rate, and I'm going 300, and I'm covering 380 of those units. I'm traveling 380 of those units. How long? How many minutes? Who said that? 142. 142 minutes. It's going to take 142 minutes. Okay, same rate. I'm going 300 units. How long? So the number is 112, but what does that represent?
112.
Yeah, 112 minutes, right. Okay, so remember, you just got to move that decimal point. It's got to make sense. The answer's got to make sense in context of the problem. Okay. All right, we're going to work on the back side now. We're going to spin over. We're going to start looking on the wind correction problem side and how we use that. So turn your E6B over, and let me show you what we've got here. All right, just like on the front side, all the directions are printed right here. The directions on how to do it is printed right here. Follow those steps and you'll get the correct answer every time. The formulas for what are happening is right here. True course plus or minus east-west variation equals magnetic course. Take that plus or minus wind correction angle equals magnetic heading. Plus or minus deviation equals our eventual compass heading that we would have to steer, okay? But in a nutshell, what this wind side of the triangle is doing, essentially, it's giving us two pieces of information. It's giving us these two pieces of information right here, our wind correction angle and our ground speed. And ultimately, we have to know our ground speed, because if we're doing these problems up here, if we're doing time, speed, distance problems, are we using our indicated or our true airspeed to calculate those? No. We're using our ground speed to calculate those. It doesn't matter how fast we're actually flying. It doesn't matter. Look, if we're at 40,000 feet and our indicated airspeed is 250 knots and our true airspeed is 500 knots, we are not traveling over the ground necessarily at 500 knots. Okay, that depends on the wind, right? So wind, our ground speed is dependent on wind. If I'm flying through, here's my plane, we're up at altitude at a higher, let's say we're at 10,000 feet. Maybe my indicator airspeed shows 100, but I did the calculation and we're actually doing 120 true airspeed. If there's no wind, I'm actually moving over the ground at 120 units per hour, right? If there's no wind. If I have a wind at my tail at 10 miles per hour, my true airspeed is still 120, but my ground speed is 130. So I'm moving faster over the ground. If I have 10 knots in my face, my ground speed is 110, right? So we have to figure out our true airspeed, and we know how to figure out true airspeed now. We did it on the flip side of the computer, because we can look at our indicated airspeed and know what it is, and then we can take our pressure, altitude, and our temperature and set them opposite each other, and then go inner scale, outer scale, figure out our true airspeed. Now we use that to flip this puppy over and figure out our ground speed, because now we're going to calculate wind into it, all right? So we're going to get ground speed and we're going to get wind correction angle. And all this thing is doing is giving us a wind triangle, okay? So if you're familiar with vector math, if you remember vector math back from school, a vector is nothing more than a direction with a magnitude. So that's a vector in that direction with that magnitude. If I take another vector from here and I go like this, that's another vector in that with that magnitude. Then I could take another vector and go that way, and you know, they line up. All this thing is doing is this. That's all it's doing. Here's how it basically works. Let's say that our magnetic course is in this direction right here. That's our magnetic course, and that is our true, so that's our course direction, and this is our true airspeed. We're going that number of units, true airspeed, okay? And then let's say that the wind is blowing from this direction at that many units, okay? All right, well, this then represents our ground speed. And this represents, or excuse me, here, but in the opposite direction, our wind correction angle. We have to cock the nose this way, this many degrees, and this is how many units of speed are getting taken away from our true airspeed because of the wind. So we could get out a piece of graph paper and a ruler, and we could do our wind correction angle and figure out our ground speeds with a ruler and a piece of paper. It's just doing that, just connecting the arrows. Or we can do this. We can use this. This is a whole lot easier. But all this is doing is that. Just want to point that out. All right. So let's assume we need to know a few things before we can even get to this side of the computer. Okay? Somebody read the first direction. Direction number 1 on there says what? Set the wind direction. So we need to know the wind. We need to know what the wind is. We need to know the wind direction, and what else do we need to know about the wind? We need to know the velocity. So on that, I shouldn't have erased that triangle there. The wind vector, we need to know that wind vector, which gave us the direction, the velocity, all right? What's the next thing it said? What's the next item on there?
Set true course.
We need to know our true course, okay? Now, our true course could either be, there's two ways you could do this. Our true course is the direction that we want to go relative to true north. So when you look at a sectional chart and the lines of longitude, they go between what point and what point on the globe? They go between what and what? Lines of longitude that go up and down. True north and true south. So Santa Claus's house to whoever lives at the South Pole. They go from true north to true south. And if I wanted to go east at a heading of, or at a course of 090, I would need to go 90 degrees from that line of longitude. That would be true course of 090. If I wanted to go 45, it would be 45 degrees true course. So true course is the direction, the number of degrees from true north, okay? You could also use magnetic course here. What is the difference between true course and magnetic course? But what is the difference between true course and magnetic course? How do we get from true course to magnetic course? We got to apply magnetic variation. Okay. All right. So here we're looking for, this is asking for true course, so we're going to go with true course. All right. And then what else do we need to know? What else is on there?
True airspeed.
True airspeed. So we have to know these things in order to use this guy. Okay. Where are we going to get this information? In practicality when we're out there flying. Well, ATIS will give it to us at the surface. Typically, these would be up at altitude. So we would get these from winds and temperature aloft forecast. The winds and temperature aloft forecast are going to give us the wind direction out of true north and the velocity. Okay? Where would we get true course from?
Pull it off your map.
You pull out your map and you figure out where I'm leaving from, where I'm going to, and you calculate the number of degrees between true north and where you're going. That becomes your true course. How are you going to get true airspeed? You're going to do what we just did multiple times. You're going to calculate, you're going to go through this process of calculating what your true airspeed is going to be, or should be, right? Alternately, you could also go to the pilot operating handbook and go to the performance section of the POH, and you could find at given altitudes, under given temperature conditions and given power settings, this should be your true airspeed. Sometimes the manufacturer will give you some of that information, but in absence of that, you can also do it right here. If you know with any given power setting what your indicated airspeed ends up being in your particular airplane, you could do it with this. If you're planning this on the ground. If you're flying, you can just look at it. Okay? With me so far? All right, so let's do one. Let's say that we have a true course, or let's say that the wind direction, we've checked our winds, and we know that the wind direction is, let's say, 220 degrees at 25. That's the wind direction and velocity, okay? And let's say that the true course that we want to travel, we want to go kind of southeast, so we want to go on a true course of 150 degrees, and we've calculated that our true airspeed is 110, okay? So this information, we have to come to this with this information in order to use it. So we need to know this information. And what we're trying to get out of this is our wind correction angle and our ground speed. These are the two pieces of information that we're going to get out of this side of the E6B. So let's just go through it. So what's the first direction say?
Is that wind direction under true index?
Okay, so the wind direction is 220, so I want you to take the 220, which is right here, and spin it till it's at the true index. So we're going to put the 220 opposite the true index right there. Okay? Now what? What's the next thing?
Mark wind velocity up from center.
Mark wind velocity up for center point. Okay, so I want you to look right in the middle of this clear plastic sheet. You see a little hole, a little grommet. Is that a little grommet? All right. I want you to know that unlike the other side of the E6B, which was logarithmic, in other words, the units were not even units. This side, you'll notice that that's 10 units, 10 units, 10 units, 10 units. There's nothing logarithmic over here. These units are the same number of units, okay? So from wherever your grommet is, just count up 25 units. So if it's right here, you go up 10, 20, 5 units and put a little dot or a little X with the pencil on your clear plastic sheet there. Now, what I do oftentimes, I'll tell people to do this, if you just want to slide, if you want to slide this thing so that the grommet's over the 100, in case you're bad at math, then just go up to 25 from there, put a dot. But it doesn't matter where you do it because your dot will always be 25 units above that grommet. There's nothing logarithmic about these. These are equal units. All right, everybody got that? So straight up the middle, with your wind direction here, you're going to go straight up the middle, the number of units. So what you've really just done is, with those 3 arrows, those 3 vectors I drew a while ago, what you're representing here is the wind vector arrow. It's in that direction at that velocity. So you've just indicated on here your wind direction vector and velocity. Okay? What's the next instruction say to do?
Set true course and return.
All right, our true course is 150 degrees. So now we're going to turn this until the 150 is under the true index. So we're going to go to 150 over here. 150. Okay. Everybody see that? And your arrow should be off over here now to the right a little bit. Got that? Okay. Now I want to superimpose that wind triangle right on top of what I got right here. Okay. This is my wind vector right here. It's coming from 220 directly towards me. There's my wind vector. It's this direction at that length, that magnitude. Okay. My true course is on this heading of 150. So my true course is in that direction right there. I'm not going to show a vector on that just yet. I'm just going to show that's my true course. Okay, so you can see that we've got 2 of the vectors going right here, right? All right, what's the next thing to say to do?
Slide wind velocity mark to true airspeed.
All right, I should have waited. I'll redraw it on there. All right, so now what we want to do is take this wind velocity dot or mark. So this, not the grommet, the velocity mark, and we want to slide it to the true airspeed of 110. So, oh man, I was pretty close. Just slide the card behind it until the 110 arc right here is right underneath your X or your dot. So right there. Okay. Now I'll draw this relationship back in here. There's my wind. Here's my thing there. There's my wind triangle right there. That's my wind triangle. Okay. So now what this is telling me, I've got both pieces of information here. I've got my wind correction angle and I've got my ground speed. Okay. The headwind that's hitting me is this much right here. It's basically 10, 11 knots of headwind, right on, or miles per whatever my units are. So I can find my ground speed by looking at the grommet. The grommet is at 109. That's my ground speed, 109. So it's 11 knots off. Yeah,
99.
or 99, sorry. 99, yeah, sorry, 99. It's 11 knots off. See that? So this arrow represents my headwind component right there. And then I can see that the number of degrees that I am over here, you see this? Where's it at here? How many degrees off to the side is my dot? I'm going to get this out of the way. What degree line does that dot fall on? It'd be 12. Be careful here because this is 20. So that means this is 2, 4, 6, 8, 10. Sometimes it represents 1, sometimes it represents 2. You have to just look at the scale, right? So 12 degrees. So the wind correction angle is 12 degrees. Well, 12 degrees what? Am I going to add that or am I going to subtract that to my true course? My true course was 150. So is it going to be 138 or is it going to be 162? You don't have a tailwind, you have a headwind. But what's happening to the airplane? So the wind correction angle is saying this. I'm flying in this direction. The wind is coming like this, therefore I have to crab some number of degrees into the wind to keep from getting pushed off course. So the wind correction angle is the number of degrees I must compensate and fly with the nose pointed over here so that I fly on this true course of 150. If I don't, then the nose will be pointed at 150, but I'll be flying over this direction. I'll be pushed in this direction. Okay? So it's 12 degrees, and it's 12 degrees to the right. So are we going to add that or subtract that? We're going to add it. Okay, and the easy, quick way to think about that, and it's really a quick and easy way to think about it, is if you draw a compass rose, if I draw a compass rose, and this is 360 degrees here, let's say, and this is 90, right? And so forth. If I'm going this way and I point the nose to the right, am I adding or subtracting from 360? I'm adding. If I go this way, I'm subtracting. So if the wind is coming from your left, if your wind correction angle is from your left, you're going to subtract it from your true course. You've got to point the nose left. If the wind's coming from your right, you've got to add it to true course. It says it on there too. Hey, right here. It says it here. Wind correction angle left, variation east, right, and I believe it, yeah, down here it says it. If you look right down here, it'll tell you if you forget or something. Well, let me see if I can get this to. It's not playing well with me here. There we go. Right there. Right here. Minus right, add left. Or whatever. Okay, let's do another one. I'll let you guys go through this one. Let's say that we have a wind direction of 180. We have a velocity of 15. We have a true course of 155. And we have a true airspeed of 125. What's the ground speed and what's the wind correction angle?
Obviously, these things are different.
What's
I
that?
mean, what you're displaying up here is very different. I don't have any of that writing on my outer.
Let me see.
Yeah.
What do you mean you don't have any of your writing?
The
Well,
WCA
like
like
variation east.
Oh, you don't have it on yours? Ah,
It's all this stuff here, right?
no, that's different. Oh yeah, you got it here, right here.
Oh,
It's right there. Yep.
Okay.
See the WCA correction
All right.
plus R minus L.
Yeah.
Yeah, you got it there.
Okay. It's just a little different.
Yeah, it's just in a different place on yours, I guess, or something. All right, so then we got true course 155. 25. All right, what do you come up with for ground speed?
111.
Yep, about 111. And what's your wind correction angle? And is it left or right? You're adding or subtracting it? Yeah, about +3. About +3 degrees. Okay, see that? Okay. All right. Let's
Is that
assume.
red dot from a previous problem?
Yeah, because on when I do it on there, I can't till I get
Yeah, yeah.
too many. They stay on there. I don't know how. Actually, I probably should be able to get rid of them. I don't know how though. Yeah, as I start clicking, they just start putting dots. There it goes. And that went away. Okay, let's take one more break, and then I'm going to give you a bunch of I'm going to give you a problem that's going to require a real world type problem that will require you to go through the whole process. Start on the other side, figure everything out, come around, get your ground speed, your trigger speed. I mean your wind correction angles and all that. Okay, so we're going to go through. I got a bunch of these. We're not going to get through them all, but we'll go through as many as we can go through. So let's see if we can work this out. So we have done enough practice in all of this for you to be able to figure all this stuff out based on the information I gave you. So see what you can do there. Just try and work this out. So here's what's given to you. And we're trying to figure these things out. Density, altitude, true airspeed, true altitude, wind correction angle, ground speed, true heading, estimated time en route, and how much fuel we burn. So this is a real world kind of a cross country planning scenario.
What was TH for?
True heading. True heading. So that's taking your wind correction angle and adjusting it. Give everybody a few minutes to work through that, and then we'll go through it together. We'll throw another one up there. I was going to make it a bit harder, and I was going to give you an altimeter setting and an indicated altitude and let you figure out what your pressure altitude is using that formula, but we'll just leave that out of that for now. I'll give you the pressure altitude. Just want you to know it's difficult for me to stand here and not talk. It's really, really hard for me to not say anything while I'm
What
standing.
was DA again?
DA is density altitude. I get in front of people and I just want to start talking.
Sign of the true teaching.
Start telling jokes.
And start telling jokes, yeah. Oops. Is anybody stuck? Or is everyone kind of moving? You're stuck? All right, so the first thing you're looking for is density.
I have those two. I
Oh.
forgot what true ACT means.
Here? True altitude. So you're going to use this
Oh,
side.
that was a C. That was,
Oh, sorry. Yeah, altitude, sorry. So true altitude, you're going to be using this side right here. Let me write that so it's more clear. My handwriting gets a little crazy. True altitude. Anybody stuck in any area, or is everyone moving? Okay, good.
What is CAS?
CAS is calibrated airspeed. So, for purposes of this, you can think indicated airspeed, calibrated airspeed. For what we're doing here, straight and level cruise flight, they're going to be the same thing. Close enough to the same thing.
Were we supposed to have it out?
I gave you a pressure altitude here, PA 3,500 feet.
Oh.
Got it? Who's done? Okay. Okay, I want to start putting answers up here. Okay, density altitude is 2,500 feet. True airspeed is 88. True altitude is 3,100. Wind correction angle is -9. Ground speed is 92. True heading is 1. Estimated time en route is 88 minutes, and you might be off by a minute or so. If you're within a minute or so of me, we're close enough. 5.1 gallons. Okay? If you didn't get through the whole thing, if you got however far you got, did you get what I have up there? Or does somebody have, do you have things that are way off of that? Okay. Okay, let's do one more. Maybe a couple more, depending on how fast you get them. Does the flow of it, do you understanding the flow of how to get I mean, it may take you a little longer than others, but the flow of getting it, all right? All right, let's do this next one. We'll do this one kind of together for those of you that maybe aren't getting it and are not wanting to say that you're not getting it. So let's just do it together here. Let's say we have, let me do the next one here. We got a temperature of 20. Okay, we have a wind direction of 180. We have a wind velocity of 25. We want to go northwest on a true course of 330. We have a calibrated airspeed / indicated airspeed of 125. We're traveling a distance of 335 units, statute or nautical, whichever. We have an indicated altitude of 8,000, we have a gallons per hour of 12.3 gallons per hour and a pressure altitude of 9,000 feet. Okay? That's what we got. So let's work this one. We're going to work this one together. All right, so we're starting out. First of all, we want to get density altitude. Let's just start with density altitude. How do we get density altitude? What do we need? What are we doing over here to get density altitude? We're adjusting for what? Temperature and pressure, and it's altitude or density altitude is over here. That means we're using this set of directions here. So these boxes deal with this. These deal with this. Density altitude over here, okay? So we're going to set pressure and temperature opposite each other. So temperature, we said, is 20 degrees. Pressure altitude is 9,000 feet. So we're going to put 9,000 feet right here, opposite plus 20. So let's do that first. And we're going to get all of the information out of that we can get before we spin anything else. We're going to put 9,000 opposite 20 degrees. Okay, my computer is froze up here. Let's see if I can go back and, yeah, I'm frozen there. All right, so I'm going to do it with this computer. 9,000 opposite 20 degrees. Okay. And when we do that, what do we read for density altitude? What do you see for density altitude? 11.5. Do you see that? Put 9,000 opposite 20 degrees. Right here.
It's behind the.
9,000 opposite 20 degrees. That's 50. So 1020. 11,500 for density altitude. Okay, see that? So density altitude is 11.5. Okay, don't spin the dial because we got another piece of information that's staring us in the face there. Our true airspeed. It's right there. Let's just read it before we spin the dial. Our indicated airspeed or our calibrated airspeed is 125. So that means what is our true airspeed? I turned the dial. Hold on. Mine moved. Let me reset it here. 9 minus 20. So 125 is 149. Everybody see that? So our true airspeed is 145, or 9, sorry. 149. All right. True altitude. Now we're going to set our pressure and temperature over on this side to get the altitude equation side. So 9,000 opposite 20 degrees on this one over here. 9,000 opposite plus 20. Okay. And if our pressure altitude is 9,000, what's our true altitude?
700.
I see 700, but 97, yeah. Okay, so I see 9,700. Okay, all right. Wind correction angle. Now we're going to flip this guy over. Get a wind correction angle. We're going to go to this side. So our wind direction is from 180, so you're going to put 180 under the true index. Just read the directions here. Mark your wind dot up. What's the velocity of the wind? 25 units, so go up 25 units and put a mark. See if I can get that wind. See if I can get my thing back here so I can follow along with you guys. There we go. Okay, here we go. All right, so we're going to go to 180 first. Wind velocity is how much? 25, so we'll come up 25, put a dot, there's 10, 25 right there. Then our true course is 330, so we spin 330 under the index. 330 is right here. All right, so right away, do I have a headwind or a tailwind? Tailwind, because the dot's behind my ground. This is my airplane. So I got a tailwind coming from my left. I can see that right away. Okay. Now I'm going to slide the card behind it such that my true airspeed is behind my dot. My true airspeed is 149. We calculated that before, so 149. So we're gonna slide this right there. So my dot is on the 149 wind arc. Now I've got two pieces of information. I've got this and this. My ground speed, we read it at the wind dot, or at the, at the grommet. Where's the grommet at? 171. There's my ground speed, 171. And what's my wind correction angle? -5. Let me move this over a little bit so we can see. Okay, -5. All right, so now I can calculate my true heading by subtracting 5 from my true course of 330. So my true heading would be what? 325. Now I need my estimated time en route. Well, I have my ground speed now, 171. So flip it back over. You have your rate. Your rate is 171. Come back here. We're going to point our rate at 171. It's going to be right about there. So we got our rate at 171, right about here. What's our distance? 335. So 335. 3, 31, 32, 33, 35, right there. How many minutes is that? 118 minutes or so. Okay, about 118 minutes. So almost 2 hours. Okay. And then how much fuel am I going to burn? Well, I'm flying for 118 minutes at a fuel burn rate of 12.3. So I'm going to burn 12.3. I'm going to put my index, my rate index on 12.3. Right about there. So my rate now is 12.3 right here. There's my rate at 12.3. I'm burning for 118 minutes. So 118 minutes is where on here? Well, this would be 100. This would be 110. This would be 120. So 118 will be right here. So how much fuel? 24 point something gallons. What's that? Point what? Point 1, 24.1. Okay. Okay. See how to do that? So you have to find you have to get some answers before you can get to the other answers, right? You have
With
to
the ET.
estimate time en route. Yeah, estimated time en route. So we're planning this. Now, when we actually go fly, you're going to, with your whiz wheel, you're going to calculate your actual times en route, which then will adjust your actual ground speeds, which will change everything as you go. But you got to plan for something to start with, right? All right, let me put another one up there. All right, let's say, okay, we're going to do a temperature now of -10, a wind direction of 30, velocity of 5, a true course of 150, an airspeed calibrated of 145, distance of 80, a gallons per hour of 5.5, and a pressure altitude of 6,500. Okay, there you go. Here's the attendance sheet that we've all signed in already, so. How you doing, Maddox? Getting it? Okay. Okay, anybody stuck anywhere that I can help out with, or is everyone rolling? Okay. How are we coming? Hey, Joseph, how you doing? Getting close? Raise your hands if you're close. If you're close to being done. Good. Okay. All right, let's start seeing what we got. Okay, somebody give me density altitude. How much? 5,000. Everybody got 5,000? Okay, then I must have done some. Oh, density altitude. Sorry, I was looking at the wrong thing. Yeah, 5,000. Looking at the wrong number. I had something different. 5,000. All right. What about true airspeed?
5.6.
Let me hear it from
153.
153. Anybody? 156. Anybody get something different? 151. 158. 164. Okay, it's 156. So if you're close to that, then you're pretty good. 156. All right. True altitude. 6,400. 6,250.
I got 57.
57. Oh, you got what?
62.
Wow, we're all over the place on this one. 62. Okay. I got 72. What do we get? What do we do? What did I put up there wrong?
We got 7,000.
You got 7,000?
You did.
I got 7,200.
I got 60.
I got 7,200. Let's do that one real quick just to see what it's supposed to be. All right, what was the temperature? Temperature was negative 10 and pressure altitude was 65. So negative 10 off opposite 65. Let's just see what we do wrong here. Somebody got stuff wrong. Might have been me. What did I just say? 65 minus 10. Okay, 65 minus 10 is there. 65 would be about there maybe? Does that look right?
Well, wait a minute. No, that's not right.
Uh,
We're looking for
Looking for true altitude,
true altitude.
right? And do I have this right? 65,
65 should be,
negative, oh, I'm on the wrong side, sorry. Negative 5, sorry. Negative 10, I mean, sorry, went the wrong way. Negative 10's over here. 65 is right about there, maybe? something like that, okay. And then so 65 here, okay, so when I did this before, I did it wrong. It should be 64. Or 62, sorry, yeah, 62. 62. So did you guys get around 62? Okay, so when I wrote it on here, I did it wrong. So 62 is the correct number. So I'm glad we checked that. And let me make a note on here to go back and correct this. 62. We'll borrow this pencil right here. What's that? Pressure altitude is what you base it off of. All right, wind correction angle. What'd you get for wind correction angle?
2, 3.
Plus or minus?
Minus.
-2, -3. Anybody get -3? Anybody get anything wildly off of that? Okay, -3 is what I came up with. Okay. What about ground speed? What'd you get for ground speed?
159.
159, 158, 161, 156. Do we have any? 160, 160. No, okay. All right, I had 154, but mine, that could be, we could go through and figure out exactly. True heading.
147.
147. Anybody gets anything different from that? 147. Okay. 147. All right. Estimated time en route. Now this one's going to differ a little bit because we had some different ground speeds, but they should be pretty close. So how much?
31.
31. Anything far off of that? That's what I got. 31. All right. Fuel burn. How much fuel do we burn? 2.8. Okay, 2.8. That's what I got. All right. We'll do one more and it'll be time to go. One more. I'll throw one more up there for you. Okay, let's see. All right, we are looking at a temperature of 0, wind direction of 150, a wind velocity of 35, a true course of 140, an airspeed, calibrated airspeed of 130. We're going a distance of 150 units. Our gallons per hour is 9. Our pressure altitude is 12,500. Okay, there you go. All right, how's it going? 1 done, 2 done. Getting faster. Well, that's a good point. All right, let's start working through them. So here's where we're gonna do this one. If you want to answer, raise your hand. If not, I'll just pick on people. If you have, and if you don't, if you don't have them all, that's fine. If you have the first one and you want to answer, raise your hand. What is the first one?
I got 13.5.
13.5. Okay, I had 13.8, but with that such a small thing to read, that's good enough. So 13.5. All right. Who's got true airspeed? Raise your hand if you want to answer. Bill, what's true airspeed? 160. Okay. True altitude. Who wants to answer true altitude?
I got
1200.
1200.
13
I got
13.
1300. I got 13,000. 13,000.
It's closer to 13,000. You just read the number wrong.
Okay, good.
13,000. It's 12,700, but that's good enough. So we'll call it 13. Good enough. All right, wind correction angle. Raise your hand if you want to answer wind correction angle. Jazz, I know you want to answer one, don't you? No? Okay. Who wants to answer one? Go ahead. +4. Okay, I had +3, but that's good enough. That's close enough. Ground speed. Who wants to answer ground speed? Okay, ground speed? How much? I didn't hear you. 125. No, I don't have 125. You got 125? Okay, then I must have done something wrong. You got 120. Okay, then I'm going to go. Enough of you are on 125, then I'm going to go with that. It's very possible I just got something wrong on here. So with 3 or 4 people answering that, I'm going to go that that's right. Okay, true heading. 142, 143. Okay, estimated time en route. Mine's going to be way off since I had a wrong ground. 71 minutes, 71 minutes. So, okay, I had 95, so because I had the wrong ground speed. Okay, fuel burn. My fuel burn's going to be off. What's your fuel burn? 10.8, 10.6. You didn't get that far? 10.8, 10.6-ish.
Can you show how to do the last two?
The AT and fuel burn? Sure. All right, so what was the actual ground speed? Because I had the wrong ground speed. 125. So that's our rate. That's our rate. So what is our rate thing that we're looking at here?
Ground speed and not true.
So you're going to put the rate on 125. Point that at 125. Oh, thank you. All right, so let's we're gonna turn our rate indicator, our 60 rate indicator, to 125. Okay, and what are we looking for? We're looking for estimated time en route. Okay, ETA. What's our distance? 150. So we're going 150, so it's going to take us 72 minutes. Okay, and now we're doing fuel burn. That's also a rate, right? Who was asking? You were asking the question.
Yeah, I did true airspeed instead of ground.
Okay, all right. Everybody get it? Everybody kind of following along? I'm going to have to go and redo these. I've made some errors on that one, apparently. Okay, so I would encourage you, if you borrowed an E6B for me, please put it back in the package, leave it on the table, and I'll get it. Next week, we're doing navigation. Okay, so we're gonna bring all of this stuff that we did today into an actual navigation navigating problems, cross-country flight planning and whatnot. So bring your E6B if you have it, bring your plotter, and if you have a sectional, bring a sectional. If not, we have sectionals you can borrow, but if you have your own, bring your own. Okay? Oh, I forgot. God doggone it, I forgot to talk about this. Let me talk about this real quick. We have partnered with Gold Seal Ground Schools. It's an online ground school. It's called Gold Seal. We partner with them now. So we are incorporating their online ground school into our program. So it will tag on to our flight training and this ground school. Okay, so if you're getting ready to take your check ride, there's no sense potentially in getting this. But if you're not and you haven't got an online ground school, then I'm going to encourage you to get their particular ground school. The 1 year is $300 from them. Not 1 year, lifetime is $300. We're reselling it for $240 if you want to buy it. But at any rate, here's how it will work when you have that ground school. If you don't already have an online ground school, all of our flight levels, we have a key that will tell you if you're on this flight level, go to their online training course, go to this module, watch this, and this while you're in this level or prior to this level. When you come to the ground school, when the emails go out, we will say on those emails, if you have the Gold Seal Ground School, go to these sections and modules and watch all these in preparation for the ground school. So it's just one more avenue to help you guys get this knowledge in your head. A lot of you do your own online ground schools. A lot of people, use Sporties or King, or everybody does different things. And what I want to do, the reason I partner with Gold Seal is so that I can get everybody on the same page, right? And then and the other thing we can do as instructors, we can see what you have studied in your ground school. We can see the quizzes you've taken. We can see the scores you're getting. We can see how you're doing in your ground school study, and it'll help us incorporate it into the flight training and ground training, okay? So if you don't have a online ground school yet and you were going to get one, then get this one, okay? All right? See you next week.